welcome back to another short CHEM271 tutorial. This one's just going to be about the mechanism of chymotrypsin. So essentially what we see in the chymotrypsin enzyme active site is we see these 3 amino acids here. So what chymotrypsin is doing is it is going to cleave a peptide bond, usually next to an aromatic amino acid. So in order to do this and catalyze this reaction, in the active site, 3 amino acids, so serine, histidine, and aspartate. So essentially what's going to happen is the aspartate has a negative bond at this pH, so it will be able to hydrogen bond to the histidine, and the histidine will hydrogen bond to the serine. So what this does, so the serine here, this is going to be our nucleophile, right? So the serine is the nucleophile, and the aspartate will orient the histidine such that it can have this hydrogen bond here, and the hydrogen bonds stabilize everything, and they also increase the basicity of histidine. So essentially histidine is going to act like a general base throughout this mechanism. A general base works the same as any other base. It will deprotonate something. So in this case, it will deprotonate the serine in this mechanism. For the sake of this tutorial, I'm just going to simplify this. So the aspartate never actually interacts in the mechanism. It just stabilizes things. And the only thing in the histidine that will do anything is just this nitrogen here. So I just show that nitrogen with the double bond, leaving out the rest of histidine. I wouldn't recommend doing this on an exam, but it's just to sort of simplify the visuals here. Okay? So steps 1 to 4. Here I just show steps 1 to 3, because step 4 is just this leaving the active site. So steps 1 to 4, though, your textbook shows 8 steps. Acylation. So this is the formation of the acyl enzyme. So an acyl is essentially carbon, oxygen, R group, bound to something else. So here we have oxygen, R group, bound to the oxygen, okay? Oh, so this group right here is the acyl. So to make the acyl, what has to happen is a peptide has to enter the active site. So what's going to happen here is this nitrogen, once the peptide is active from the histidine, so the peptide has entered the active site, nitrogen from the histidine, this lone pair, what it is going to do is it's going to come and steal this proton. So here, histidine is equal to a general base. Okay, so histidine is a general base because it is deprotonating the OH off the serine. So now the electrons in this bond have to go somewhere. So what they're going to do is do a nucleophilic attack on the carbonyl of the amide in the peptide backbone, and then the electrons will come up on top of the carbonyl, okay? So what's going to happen here is the peptide will covalently bind. So covalently binds the substrate. Okay, that's pretty common to see. Anything else here? So essentially, when the histidine removes this hydrogen, this makes an O minus. So O minus here, this is a good nucleophile. So it's a good nucleophile, so it is able to do a nucleophilic attack on the peptide. Normally, the OH is not a very good nucleotide, so that will not be able to do the nucleophilic attack. But when it is deprotonated and activated by the histidine, it is able to do the nucleophilic attack. Attacks carbonyl, yeah, and this is a general base because it is a proton acceptor. I think that's everything here. So now at this step, what we see here is that the chymotrypsin active site has this sort of thing here. This is called the oxyanion hole. So this is going to stabilize this sort of intermediate structure by creating this sort of positively charged little pocket of the active site that this negatively charged oxygen that used to be the carbonyl can then go and bind to. Okay, so the oxyanion hole is actually made up of glycine plus serine, and the positive charge comes from these NH bonds, which have a delta plus on the hydrogen end. So these delta plus here, so delta plus, these are able to sort of make some positive charge in this pocket and stabilize this O minus. Okay, so next up, what's going to happen here? So we see the histidine is now protonated. So now what's going to happen, this negative charge on the oxygen has to do something. So it's going to come down, reform the carbonyl. But now this carbon, after it does that, would have 5 bonds. Carbon cannot have 5 bonds, so one of these bonds has to break. What breaks is this amide bond here. So what this amide bond, the electrons in this amide bond are going to do is they are going to come and they are going to steal this proton from the histidine and then give the electrons back to the nitrogen in the histidine. So this is going to break apart this, and it's going to give the nitrogen an extra hydrogen. Okay, so this is essentially cleaving off part of the peptide. So it's gotten rid of the peptide. Okay, gotten rid of part of it. Some of it is still in the active site, forming this acyl group. Okay, so what is happening here? So essentially, this amino, this N here, this amino group is going to be protonated by the histidine. So this essentially becomes NH, so nitrogen with 2 hydrogens in our group in this carbon. So 4 bonds, that gives the nitrogen a positive charge. The nitrogen doesn't want the positive charge, so it is able to leave. So we can just write NH2R with a plus, and then the COR1. So this sort of is a good leaving group. Okay. The other thing to mention here is that histidine, so here was a general base. On this step, it's a general acid. So histidine with the hydrogen, this is going to be general acid. Why? Because it donates a proton. So it has a proton, it becomes deprotonated by donating the proton. So a general base, what we observe there is a proton acceptor. So it takes the proton, here general acid, this is a proton donor. All right, so now essentially we've cleaved the peptide bond using the nucleophilic serine, and now what we're left with is just this acyl group with only one of the R groups present, so only one side of the peptide chain. The other part of the peptide chain has been cleaved off, and now it can leave the active site. So that's the acylation steps. So next we will look at the last steps, which are deacylation. All right, continuing where we left off. So these are steps 5 through 8. Okay, I'm just excluding step 8 because step 8 is just this leaving the active site, but this is what's given in your textbook. So these represent deacylation, or the removal of the acyl group, which remember is R, so the carbonyl with the R group, from the active site, okay? So let's look at the mechanism for this. So remember the full thing here, the aspartate, the histidine, and the serine. So the serine has the acyl group. So now we begin the actual hydrolysis step. So the hydrolysis step is where we use water to remove the cleaved peptide chain from the chymotrypsin active site. Okay? So what's going to happen in here is the water is going to enter the active site, and then the histidine here is going to act like a general base. It is going to take the proton, so general base proton acceptor, and then the electrons in this bond, what they are going to do, come and bind to the carbon there, and then the electrons in the carbonyl go up to the oxygen. So, so the water is going to enter the active site here where the amine was, the amine that left the active site, okay? So histidine is going to be our general base. It's going to deprotonate H2O, and then H2O here is also our nucleophile, and this will attack the carbonyl. Okay? So, when we've done that, we now have a carbon with 4 different bonds, and the oxygen with the negative charge, that was the carbonyl. This is now back in the oxy anion hole. All right, so now that we have this, what's going to happen is histidine can now act as a general acid again. This is very similar to last time. So the negative charge goes back down, reforming the carbonyl. Carbon now has 5 bonds, so we have to kick something out. In this case, we are kicking out the serine. So the serine is going to be kicked out. This is going to come and pick up this proton from the histidine. We make the serine a little better. Okay, and then the electrons from the NH bond are going to go back to the nitrogen on the histidine. So summarizing what's happening here, histidine is going to be a general acid. It is going to be deprotonated in this case, like an acid, and then the serine itself is going to be protonated, and the serine is also going to be our leaving group. Okay, so the protonated serine can be kicked out from the carbon, right? And then what's left is we've reformed the active site, and our cleaved peptide can now leave the active site as well. So that is it for the chymotrypsin mechanism. Thank you for watching.